Hello, this is video number 31, and this is chapter 6, section 3, and it is covering adding and subtracting radicals. Okay, so when you add and subtract radicals, it's similar to adding and subtracting variable terms in that you can only add and subtract like terms, right? That's a common thing in math. And by a like term, when we're talking about radicals, so like terms, so radicals are like terms when the coefficients, there's an S on there, coefficients are like, meaning numbers and or variable combinations, and the radicand, what's underneath the radical, must also be like. Okay, so here's an example of like terms. Let's go 6x squared y radical 3y and 14x squared y radical 3y. So these have, if you look at them carefully, exactly the same variable combination outside. So x squared y, and then underneath the radicand, they have the same information, which is a 3y. So these are considered like terms. Let me show you an example of not a like term. So we might have 6x squared radical 3y and 6x squared radical y. Nope. Pretend I didn't even say that. X squared radical 3. Okay, so what's happening here, you have the same variable terms on the outside, but you do not have, these are not the same underneath. And so you cannot combine these together. They would have to stay as two completely separate terms. Okay. Now, if you are adding them together, take a look at the problem up above. If they are like terms, you simply add and subtract the coefficients. So in this problem up here, if I have like terms, which I do, all I'm going to do here is add the 6 and the 14, and then this chunk that's the same on both of them gets written one time on the answer. So the answer to that would be 20 x squared y radical 3y. That would be the answer to that problem. Okay? So we're going to work through just a couple of these. This will be a super short video. If you got the handle on simplifying, then this is pretty straightforward. All right, so varsity starts out asking you some very straightforward things that you're just going to add together. So if you had the problem 5 radical 10 plus 3 radical 10, the first thing you're going to do is to check to see if the radicand can be simplified? Well, this one we can't because we know a rad 10 goes to a rad 2 and a rad 5. Nothing pairs up. They stay together. So these would just get multiplied back together and you end up going back to where you started from. So all you have to do here, if you check to see that the radicands can be simplified, do it if you can. If you can't, if you have like radicands, oh geez, things are moving all over the place. Then just add or subtract the coefficients. Oh, that's an E. FF efficients. Yikes. Okay, so here we would just add together the 5 and the 3, and we keep the radical part, and the answer to this would be 8 radical 10. Okay? Super straightforward if they're like terms. The next one, already like terms, 8a rad 7 minus 4a rad 7 plus 6a rad 7. So first check to see if your radicands can be reduced, and they're prime, right? And they're all the same. So they're prime, they can't be reduced, they're all the same, which means we can add as long as our coefficients are like terms, and they all have a single a in them. So we're just going to add these together and say 8a minus 4a is 4a plus a 6a is 10a radical 7. Okay? Now, they're not always going to be quite so nice and straightforward looking. So what happens if you get one that looks like this? 5 rad 80 minus 3 rad 45. You might want to space these out a little bit on your paper. Plus 4 rad 180. Well, the only thing you really need to be careful about here is when you simplify these, you're going to simplify all of them and then see if you can add together. So you're going to simplify first. You can't simplify, like you can't take a radical from the first term and combine it with a radical for the second term. So I want you to kind of make this little wall down in between. I'm going to make this little wall here that you're going to keep things inside the walls, and you're not going to cross over the walls as you reduce. Okay, and I'm going to do all of them in a different color so it's real easy to see what's happening. So I'm going to reduce the rad 80, and I'm going to go rad 8, rad 10. The 8's going to reduce to a 4 and a 2. The 10's going to reduce to a 2 and a 5. The 4 is going to reduce to a 2 and a 2. And now I have a 2 there, a 2 there, and the 5 can't come out. And don't forget the 5 at the beginning. So I have the 5's going to come down. This 5 is coming down, and I'm multiplying by each of the 2's, and then anything that is left in a radical. So this is 5 times 2 is 10 times 2 is 20 radical 5. And then I'm going to bring down this minus sign. Okay? Then we're going to reduce the next one. 45 goes to a 9 and a 5. 9 goes to 3 and a 3. Those get circled. This 3 is going to come down times this 3 that we're taking out. And we have a radical 5 left over. So this gives me a 9 radical 5. Bring down the plus sign. And then I'm going to reduce the 180, which I'm going to go 18 and 10. 18 is 9 and 2. The 9 is 3 and 3. The 10 is 2 and 5. All right, so I have the 4 from the front. Pair of 3's become a 3. Pair of 2's become a 2 out front. And the rad 5 that's left over. And this becomes 4 times 3 is 12, times 2 is 24. Radical 5. Now, all my radicands are the same. So my answer is going to have a rad 5 on it. And then I'm going to go 20 minus 9. Well, that's 11. And 11 plus 24 is 35. And that's the answer to that problem. Okay, so you just reduce each one separately. Take your time. Don't forget things. Highlighters are handy, or using these arrows like I did, especially when you have the coefficients in there. Okay, let's do one more just as a sample to see what happens when they don't all add together. So if you start out with 3 radical 50, I'm also going to handle simplifying these radicals just a little bit differently for the people who see their perfect squares and don't know why I haven't done this yet. This is definitely an option for you. So I'm going to take my little crayon separator here, separating these terms at the signs. Excuse me. All right, so you don't have to always go to perfect squares when you reduce, to primes when you reduce these. If you see perfect squares happening in the process, you can utilize those perfect squares and simplify those instead. Here's what I mean. A radical 50 goes to a rad 25 and a 2, and the root of 25 is 5. No more radical, it's just plain 5. Or you can take that rad 25 and go rad 5, take the two of them, becomes one of them, right? It's the same thing. So I'm going to use this method that I just did on the left. If you don't like it and want to go all the way to primes, feel free to do that in your notes. You don't have to do exactly the same thing I do. I'm just giving you different options if your brain thinks a little bit differently than other kids in the class. So to finish off this left-hand one, I have 3 times 5 radical 2 is 6 radical 2. Oh my gosh, 6. Where the heck did that come from? That is not 6 radical 2. It is 15 radical 2. And then I'm going to bring my minus sign down. 32 is 16 and 2. Well, the root of 16 is 4. So this is 2 times 4 radical 2. So this is 8 radical 2. And then the root of 20 is rad 4, rad 5. The root of 4 is 2. So this is 4 times 2 radical 5, which is 8 rad 5. All right, well, what we have here are two like terms that we can put together. 15 minus 8 is 7. And then this guy is not a like term, so you would have two terms in your answer that have different radicands. And that can happen. It will happen a lot. Sometimes you'll have, when we multiply in the next video, you're going to have up to 4 terms left over. So don't be afraid if that can happen. Also, just as a side note, I thought of this while I was talking. If you ever have the root of 1, that is, a root of 1 is actually 1. So make sure you're simplifying those. And if you ever end up with a root of 0, that literally is 0. So if you had to multiply that by anything, you would still end up with 0. So make sure that you're simplifying these if you see those. Okay? All right, that's all for this one. Toodaloo.